All right, welcome back, everybody. This is going to be Chapter 6, Lesson 4, where we're going to talk about how to adjust and calculate the trim of a vessel based off of a weight shift. All right, we're going to get into weight additions and removals later, but now we're just going to start with weight shifts. So, to start off, I'm Lieutenant Timothy Mueller, and let's get started. With weight shifts, we can intuitively think if we have a vessel and we shift weight to one side, forward or aft, we know that that side that we're shifting the weight to is going to sink deeper in the water. We saw that in the transverse perspective with listing before. When we took on damage on one side, we knew that that ship, if we took on damage on this side, it would tilt over to that side. It's exactly the same way when we're looking in the longitudinal perspective. So let's look at the diagrams and kind of see through a generic weight shift problem how we can step through all the information that we're given and come up with a solution. So first off, we have to kind of think about what's happening to the ship. So if we start here, this is just our ship with a weight on it somewhere. Now, if we shift the weight forward, we know that that forward part of the ship is going to sink. And if the ship is completely rigid, we know that the aft end is going to pop up. They always move opposite of each other. So shifting forward, so going from here to the very end, maybe switching water from a service tank, maybe up to the forepeak. Shifting it forward is going to tilt the ship forward. That's going to cause a forward TM, TM being trimming moment, and we'll get to that in a second. But that is going to cause a moment to want to cause the ship to tilt or trim forward. If we shift it aft, however, so going from this position to this position, we're causing an aft trimming moment. Now, if you see in this diagram, I've made this weight cross the LCF. It doesn't necessarily have to cross the LCF. If we started with the weight right here and we shifted it to this position here, so if it started here and we shifted it here, that would still be an aft trimming moment because it depends on the direction that you're shifting, not the orientation with respect to the LCF. So keep that in mind. That's a very common mistake that people make when it comes to test time with trimming problems. It depends on the direction that you move the weight, not if it crosses the LCF or not. All right, so good. The preliminary step is done. We've taken a look at the problem and we can get an idea if our forward end is going to drop down and the aft pop up, or the opposite. The aft end sink down and the forward end popped up. Now we step through these steps that I've kind of labeled here on the board. So step one is to find our TA, or the trimming arm. This is the distance that we've shifted our weight from aft to forward or forward to aft. So we have to find the center of gravity, if we're talking about liquids, and we typically are, center of gravity of all that liquid originally, the center of gravity of the liquid in the end, and then find the distance between them. The common way to do this is find a frame number for where the center of gravity is initially and then at the end, and then just subtract the values together to find the distance. So now we've found the distance that we've shifted. That's our TA, our trimming arm. What do we do with that information? Well, we know the weight that we've shifted, and we know the distance, and we know that a moment is a force times a distance, weight being a force. You can kind of expect that I'm going to say trimming moment is something that we come up with next. So trimming moment is the weight that we've shifted times that trimming arm. Great. Now we've got a moment. We've been working with moments so much in all these lessons. Now we've gotten back to what we're used to with trimming. What do we do with that? Well, with a vessel, we have what's called change in trim. And one of the characteristics of a vessel that we get from our draft diagrams and functions of form is the moment to trim 1 inch. This tells us how much of a moment, that trimming moment, how much of a moment we have to impart onto the vessel in order for it to trim 1 inch. It doesn't seem like much, but when we start moving long tons of liquids or taking on long tons of flooding water, it actually can add up and make a very significant change in the trim. CT So we have a trimming moment, and then we have a moment to trim 1 inch, which the units of that is basically going to be moment per inch. So we have moment divided by moment per inch. So CT is going to give us inches. We have trimming moment, so let's say it's 1,000 foot long tons. And let's say our moment to trim 1 inch is 100 foot long tons per inch. 1,000 divided by 100 is going to give us 10. Then working with the units, it would give us inches. So in that scenario, we would have a change in trim of 10 inches. Now what does that mean? Change in trim, CT, is the overall change between forward perpendicular and aft perpendicular. And this is the addition, the sum, between the change in the forward draft due to trim and the change in the aft draft due to trim. And we're going to see that applied here in a second. All right, so I've thrown a couple new terms your way. So I would suggest if you haven't fully grasped it or you don't fully understand it, rewind a little bit and go back and see exactly where you're stumbling. I'm going to keep repeating these things, and I'm going to go through this process again, albeit quickly. I'm going to go through it again, and maybe that'll change your perspective on it. So we know CT is the overall change in the trim between forward and aft. And that is the summation between delta D forward, which is just the change in trim of the forward, and delta D of the aft. And that makes sense. So if we go to this diagram here, say we have an aft trimming moment, we know the ship was originally straight with zero trim, zero drag. So it was straight along this horizontal line. Then now it's trimmed. So we have a change in the draft forward, it's popped up. Then we have a change in the draft aft, it's sunk down. The change in trim is the overall change. So the overall change from aft all the way to forward. Going down to this diagram here, we see the ship originally at this horizontal position. We see the middle perpendicular, the little tennis ball symbol. Then we have the LCF right here. And the LCF is critical in these problems. Now, so step 4 is to look at exactly what's going on. We need to take the information that we got from here, our preliminary step, where we know if we're going aft or forward. Then we also have to understand exactly what's going on with our change in trim. So we have our boat originally here, and we know that change in trim is the overall change in that trim, just like it says. But it doesn't match up with what we have originally. We know that the LCF is a pivot point to the ship, which means that no matter how much we trim the ship, as long as we don't change the displacement, that LCF is going to stay right still and it's going to have the same draft no matter what we do with all the weight on board. So knowing that, we know that this here is going to be the final orientation of the ship. But we know that it has to be up at that LCF. So we just take this line here and we shift it straight up to this red line here. Now we have something that we can work with. It's something that's physically real. Now we have this red line, E to F. We had this original change in trim was the entire distance from B to C, the entire change between forward draft and aft draft. Now we've shifted it up. We see that this here, the CE, that's going to be our delta D forward. In this situation, we have a forward trimming moment. So we're going to have a delta D forward that's going to be positive. We have to say that down is positive because we know that as a ship gets deeper, its drafts increase. If we go from 11 to 12 feet of draft, we know the ship is sinking 1 foot. If the draft increases here, so if the forward end dies down, that means that the aft end has to pop up. And we see that right here around the LCF. We go down to the bow, we go up to the stern. We still have that same change vertically from E to F. That's still our change in trim. However, we've put it into an actual physical model. So we have delta D forward right here, and then delta D aft right here. And delta D aft plus delta D forward is, like I had mentioned, total change in trim. So here, delta D forward plus delta D aft plus delta D forward equals change in trim. So now we have to do some geometry, and knowing what we know about angles and a little tiny bit of trigonometry, now we can start solving delta D forward, then delta D aft by using the information that we know. Now we see a couple triangles here. We have ABC, which is that big black triangle, which I've repeated over here. Then we have a slightly smaller triangle. We have DEC, which I put right here. Now, since we're moving this line straight up, we're not doing anything to the angles themselves. We're just kind of changing the size of the sides, but the angles themselves are not changing. This angle here is the same as this angle here. This is a right triangle. They share the same angle. This angle here is the same as this angle here. So by knowing that, we know that the sine of this angle is going to be the same, the opposite over hypotenuse. Cosine adjacent over the hypotenuse is going to be the same, and the tangent is going to be the same, tangent being opposite over adjacent. If we look at these angles here, going back over here, for this angle, so now we're looking at ABC, we know the tangent is opposite over adjacent, so opposite being CT and adjacent being LBP. We've already solved for CT in step 3. We know what LBP is. That's something that we're going to be given in our prompt. We have to know how long our ship is between the perpendiculars. Next, we go into this smaller triangle. We know that these angles are the same, so the ratio between the sides has to be the same. This top side here, so if we have the ship coming up to the LCF, the length of this side right here from C to D has to be the distance from C to the middle perpendicular, which we know is just LBP divided by 2, the overall length between perpendiculars in half, plus however far the LCF is aft of our middle perpendicular. So CD, this here, equals C to the middle perpendicular, which is LBP divided by 2, plus however far aft the LCF is from our middle perpendicular. Then this vertical side, that is our delta D forward. That is how much our draft changes from original to final position. So we have LBP divided by 2 plus LCF. We have delta D forward here. We know LBP. We've already been given that in the prompt. LCF is something that we've either been given in the prompt or we can find from our draft diagram functions of form. So we know this value, this entire side length. We're trying to solve for this. If we set these ratios up, then now we can start getting somewhere. So I said the tangent was CT over LBP. If we flip that, LBP divided by CT, then take the tangent and then flip that of this other triangle, they have to be equal to each other because all the angles equal each other in these two triangles. So the tangent here is going to be delta D forward divided by this whole mess. We flip that. We have LBP divided by 2 plus LCF divided by delta D forward equals what we had for the original triangle. So now we've set up our problem to where we can actually start solving. So from 4, we go to 5. Isolating delta D forward here, bringing that over, LBP to the bottom, CT to the top. We have delta D forward. So due to a trimming moment, this is how much that forward draft changes. Equals LBP divided by 2 plus LCF, which is the length of this arm, of this distance right here from the LCF all the way to the forward perpendicular, divided by the LBP, LBP being this entire length, and then CT, which is this right here. all these things we know. So now we can calculate delta dF. Now here's where you have to be careful. Like I said before, we said that down is positive. We have to know if we have an aft trimming moment or a forward trimming moment in order to know if our delta D forward is going to be positive or negative. If our forward draft is going down, so the bow is going down, that draft is increasing, which means that delta D forward is going to be positive. If the aft end goes the opposite way, then our delta D aft is going to have to be negative. How do we find out how much delta D aft is? Well, it's just CT minus the delta D forward. CT we've already found. Trimming moment divided by moment to trim 1 inch. Delta D forward is what we've already found. However, CT is a positive number. Delta D forward is either positive or negative. You have to take the positive value of delta D forward to get your delta D aft. And that makes sense if you just look back at this diagram. We have CT here, that total length. By shifting it up, it equals the total length, because it doesn't matter if we're counting up from E to C to F or counting down from F to C to E. We only care about that absolute distance between the two. So you take your positive values and then you just plug them into this equation to get your delta D aft. I would highly suggest just keeping everything positive until you get your delta D aft and your delta D forward, and then taking a look at exactly what's going on with your ship and saying, okay, if down is positive, if I have a forward trimming moment, like I have in this problem, if I have a forward trimming moment, I know that my bow is sinking, going down is positive, so my delta D forward has to be positive, meaning my delta D aft is the opposite, so that's negative. So I know that's a lot to digest all at once. And so now we're going to go through the decision-making process and the steps one more time, a little bit quicker, and hopefully it helps you see the flow of things and it becomes a little bit more clear. So first off, the preliminary step that we have to make is, are we dealing with a forward trimming moment or an aft trimming moment? Now, if we know that we're doing forward, we know that our bow is going to sink and our aft is going to come up. We know that our bow going down is going to be positive, aft coming up is going to be negative. That's just something that we tuck over to the side for after we get to steps 4 and 5. Now next, we have to find out our trimming arm. And that's going to be the distance that the center of gravity moves, typically it's going to be liquid, from one point to another. Now that we've got our TA, our trimming arm, we know our W, the weight of the liquid that we shifted, or the weight of the cargo, whatever it might be. Now we use those two, multiply them together, and we get the trimming moment. That moment is going to help us go from step 2 to step 3. Step 3 is the total change in trim. Change in trim is going to be that total moment that we're imparting on the ship, divided by the moment that we need to trim the ship 1 inch. If we have more moment than needed to trim 1 inch, then our answer is going to be more than 1. If we don't have enough to trim 1 inch, then we're going to have an answer less than 1. Starting to be pretty intuitive. Now we have change in trim. And we know that change in trim is the overall change from the overall change between the forward perpendicular and the aft perpendicular drafts. So we started from here, they go here. This total vertical distance between the two is going to be our change in trim. Now we take that idea and we start applying it to a diagram. We know the ship's originally here. We kind of pin the ship at the stern and we move it, or we pin it at the forward and we move it, depending if we have a forward or an aft moment. Then we know that the LCF, due to a trimming moment, the draft does not change at that LCF. So we take the ship, if we went like that, we scoot it up to the LCF. Now we have triangles that we can work with. And that was what we had right here in step 4, moving into step 5. All the geometry that we did right here, A, B, C, and D, E, C, allowed us to derive this formula here at 5. This gives us our delta D forward, which is how much our draft forward changed due to this trimming moment. Then all we got to do is, whether that's positive or negative, I would consider keeping that positive. Then CT minus that value, because CT is positive. If we kept our delta D forward negative, we'd be CT minus a negative number, which would give us a positive. So it would be CT plus some number, which wouldn't make any sense. Always make sure that your delta D forward and your delta D aft, the absolute value of them, so the positive value, always equals your change in trim. It has to. That's just by definition with what we learned here in step 3. Now you have all your information to find out how much your draft changes forward and aft. If the aft goes down, that's going to be a positive. If it comes up, then it's a negative. Then you can take your original drafts. So say we originally had 10 feet of draft forward and aft. If we know one goes up and one goes down, the one that comes up would be something like 9 foot 9 inches. And the one that goes down would be something like 10 foot 4 inches, depending on the characteristics of the ship. So hopefully that a little quicker perspective kind of helped you see the flow and a little bit more clear this problem. We're going to go into an example problem right now so we can see all this in action. All right, now for the example problem, I'm going to give you a little bit of moral support, and I'm actually going to work through it with you so you can see how it's all done in real time, rather than just the answers already being up on the board. Let's take a look at our prompt. I'm going to use red, and I'm going to highlight everything that could be of information for us. So we have a vessel that displaces 3,000 long tons. That might be a little tidbit of information we might need later. We're shifting 50 long tons. Okay, I already see my little W right there of diesel fuel marine, DFM, from G at frame 340 to frame 48. Okay, it sounds like this is giving me the distance that I'm shifting my weight. So that's going to be my trimming arm. I already got my W, so I already mentally, I got my trimming moment. My initial draft forward is 11 feet 0 inches. I'm dealing with trim. I'm going to eventually probably be calculating a delta D forward. So I've been given one of my drafts. Trim is 0 and my drag is 1 foot BS by the stern. Now what does all this mean? So we start with our drag. My drag is 1 foot by the stern. So it's designed to be 1 foot deeper than the bow is. I got my bow is 11 feet. That means that my stern, with 1 foot of drag and nothing in excess, trim is in excess of drag, that means that my stern is 11 plus 1, which is going to be 12. So I now know that my stern, or my draft aft, equals 12 foot 0 inches. All right, good to know. I'm just going to underline that right there. All right, LBP equals 400. I'm definitely going to need that for trim. Frame spacing is 1 foot. Okay, good to know. Let's keep that in mind. LCF is 14 feet aft of the middle perpendicular. And then MT1, my moment to trim 1 inch, is 2,250 foot long tons. Another thing that I need. All right, so it looks like I have everything that I need. A little bit of playing with the frames there, a little tricky with the drag, but nothing that we haven't already seen or defined earlier in this chapter. So where do we start? Well, first we got to do that preliminary. We got to find out if we're moving, if we have a forward moment or an aft moment. So we know that frames increase as we walk aft. So frame 48 is going to be forward of the ship, and then frame 340 is going to be in the aft part of the ship. We're going from 340 to frame 48, which means we have a forward trimming moment, which means that our forward perpendicular is going to be down here somewhere, which means the aft end is going to pop up. All right, if we call down positive, so we say down positive, when all is said and done, we should have a delta D forward that is positive, and then a delta D aft that's negative. Let's see if that works out. So we did our preliminary. We know what we're looking for. We got positive here. We got negative here. We'll say that. Now, let's start figuring out what we need for our trim. Now, trimming arm is one of the first things we have to find. Do we know our trimming arm? We've been given enough information for it. We know we're going center of gravity from frame 340 to 48. And we've also been told that our frame spacing is 1 foot. So it's 1 foot from frame 340 to 339, another foot to 338, so on and so forth. So all we got to do is subtract 48 from 340. And that's going to give us 298 or 292, right around there. Let's see here. Use the calculator. Told you I'm going to do this in real time with you. 340 minus 48, 292. So our trimming arm is going to be 292 feet. All right, now we got to take our trimming moment. And the trimming moment is just that trimming arm times the weight that we moved. So we take that 292 times 50. We already have the amount of weight that we are shifting, so we don't have to do anything with that number. 292 times 50, that's going to give us 14,600. So this is 14,600, and don't forget your units, foot long tons. All right, now we have our trimming moment. How do we find our change in trim? Do you remember? It's up in the prompt. We have enough information. It's going to be right, where's that? The moment to trim 1 inch. We know how much of a trimming moment we have. Now we just need to find that moment that's going to trim us 1 inch. So our CT, our change in trim, is going to be the trimming moment divided by the moment to trim 1 inch. So we had 14,600. Now we're going to divide that by 2250. And we get 6.48888. So 6.49. So our change in trim is 6.49 inches. Remember, when we do change in trim, we're working in inches. Don't accidentally call this feet. This is inches. All right, so next, what do we have to do? Now we have to think about our triangles. We have our CT, we have our LBP, we have our LCF. We should have pretty much everything that we have our CT. So we have everything that we need. Now let's start drawing these triangles. Here's our ship originally, just as some horizontal. I know that we have this drag here with the trim, so our drafts are different. However, this is just a representation to make things a little bit easier for us. So if we think of the original condition just being flat, then we can change there, and visually we can see what's going on, and then apply our drafts. So we have this, and we know that our CT is 6.49. We already know we're going to be in this type of a situation, because we have a forward trimming moment, going from 340 all the way to 48. So let's draw this here. This triangle is going to have this side be CT, and this length here is our LBP, which we already know. But this line here doesn't mean anything, because we know, it means something, but physically it's not helping us. We know that the ship, because of a trimming arm, doesn't change draft at this LCF. At the LCF. So knowing that, we know that these two lines, these two ships, have to intersect right at that point. So we take this line and we just shift it straight up. See how straight and parallel I can get these lines? Right like that. So now, almost got it. So now we have something we can work with. You see this big triangle here from point A, B, C? Here, you also see the smaller triangle, D, E, C. Now remember our ratios. This length here, CD, is the distance from forward perpendicular, so 0, to the middle perpendicular, which is going to be LBP divided by 2. So this frame here is 200. and then the LCF is just 14 feet after that. So this distance here is just 214. So that's 214. The overall length is 400. This CT right here is 6.49 or 6.5. All we're looking for is this right here, CE. This is going to be our delta D forward. And here is our delta D aft. We'll get to that in a second. So now we got to find our delta D forward. Delta D forward equals the ratio between this length and the overall. Like I say, you just think of it like a lever. Think of that boat, you know that longer arms, the very tip of a longer arm is going to move further than a shorter arm. So keeping that in mind, delta D forward equals my lever arm. So it's going to be LBP divided by 2 plus LCF divided by the entire thing, which is going to be LBP. Then I'm going to multiply it by CT. So I just want to find the ratio of this arm to this arm is going to be the same as the ratio of this to this. So applying that, I now have 214 divided by 400 times, CT was 6.49. That's going to be right around 3.5-ish, something like that. So 214 divided by 400 equals that, times 6.49, or 3.47. So this here, 3.47 inches. Remember, when we're dealing with drafts like this, we're dealing with inches. So great. Now we have delta D forward. We're going to keep this positive for now, and then we're going to take a look at the overall situation we have and see what needs to be positive and what needs to be negative. Now we know that change in draft is 6.49. We know that delta D forward is 3.47. Now we got to find this delta D aft. And you've probably already noticed in previous diagrams, this distance here, this delta D aft, is the exact same as this distance right here. Because we took that line and we shifted it perfectly parallel straight up. So if you want to think of it like that, we have a delta D aft right there. So now all we've got to do is this distance minus this distance is going to give us this distance. So we take our 6.49 minus 3.47, and lo and behold, we get 3.02. So now our delta D aft here equals 3.02 inches. We're going to double check ourselves. We're going to add the delta D forward and delta D aft together and make sure that we get our CT. 3.02 plus 3.47 is 6.49. Boom, right there. We're right. Now we have to take a look at the diagram and see what's positive and what's negative. Now, do you remember which direction is positive? It's either up or down. It's down. So whatever side is going down, that is going to be positive. We know that we have a forward trimming moment, moving from 340 to 48. Bow is going to go down. Delta D forward has to be positive. Delta D forward is right here. That's going to be positive, which means my delta D aft is going to be negative. Now I apply these changes to my original drafts. I knew that my forward draft was originally 11. I know that just doing some work with the drag, my draft aft was 12 feet. So delta D forward, I'm going to go down a little bit. So 11 feet, 0 inches plus 3.47 inches. We'll just round that up to an even 3.5 inches plus 0 feet, 3.5 inches equals 11 feet, 3.5 inches. Great. Now I got to work with my aft. My aft was 12 feet. So let's just kind of circle that and isolate it. I had 12 feet 0 inches. And now I'm subtracting from that. We're going to round this down to an even 3. Minus 3 inches equals that. Can't take 3 from 0, so I got to make this 11. 1 foot is 12 inches. Taking 3 from 12, that's going to give me 9. 9 inches, 11 feet. So my new draft aft is going to be 11 feet, 9 inches. Now, how can we check ourselves here? We originally had 0 trim. Now we imposed a change in trim of right about 6.5 inches. Does that actually work with what we have? So we had our drag was 1 foot. So if we take our forward draft, add a foot, that's going to be the stern with no trim, and then we impose that change in trim, we should get what we've already gotten for our aft draft. So let's see. We take our forward draft, yes, it's forward. Take our forward draft, 11 foot, 3.5 inches. Then we add a foot, so with drag with no trim. Add a foot, so now we're working at 12 feet, 3.5 inches. Then we're going to impose 6.5 inches, just rounding that straight up to 6.5, of change in trim. But now we know that our change in trim makes our our aft higher. So we have to subtract 6.5 from this to check our answer. So 12 foot 3.5 inches minus our CT, which is going to be 6.5. Cancel out the 0.5s. Then we have to move out another one here, and that's going to give us 11 feet 9 inches, which is exactly what we needed in order to check ourselves from forward, apply our drag, then apply our change in trim from 0 to 6.5, and we get exactly what we needed to check our answer. So that is how you do a trim problem in relatively real time. Just go through the steps, and I would suggest if you don't fully understand where I was coming from, just think about this triangle here. When we shift that weight up, we shift this line up, our CT gets split into delta D forward and then delta D aft. But because it's parallel, we can just shift this delta D aft right there. So just think of it like that, and it'll be a little bit easier for you so that you don't have to memorize these formulas. I'm not memorizing any of these formulas. I'm just understanding how moments work with each other, and then just these similar triangles. There's nothing any more complicated than that. All right, so that does it for this lesson on trimming with weight shifts. When it comes to weight additions and removals, it's exactly the same as a weight shift. However, we have to add that weight on or remove it. There's a very quick trick that we can do. So all we have to do is one more calculation on the forward end. And then when we calculate our final drafts, we just do another calculation there, and there's no difference. All we're doing is adding weight or removing weight from the LCF. So we have parallel sinkage or parallel rise, and then we do our trimming. And trimming is nothing different than what we've already done here. So when we get to that video, you should be relatively happy. Until then, I'm Lieutenant Timothy Mueller, and I hope you have a great day.